Welcome to This Explainer. I'm absolutely thrilled you're here. Today, we're setting the stage for a really fascinating dive into how we can manipulate basic, everyday physics to tackle one of the biggest issues of our time, the global energy crisis. We're going to literally look under the hood at the mechanics of motion and see how some incredibly clever engineering might just change the entire way we power our world. Okay, let's dive right into our roadmap for today. We'll be covering the power generation challenge, torque, power, and RPM, the fuelless generator system design, EV motors and power curves, and finally, redefining sustainable energy. Section 1, the power generation challenge. So, before we look at the actual machines, we really need to understand the massive problem driving these engineering innovations in the first place. To frame our whole exploration today, I want you to chew on this question for a second. How do machines balance brute force with speed to do incredible work without just wasting energy? Optimizing that exact relationship is the absolute core of maximizing efficiency. And that's true whether you're turning a massive generator or just accelerating an electric car down the highway. Because let's be real, right now we're facing a profound global power crisis. The researchers in our source material highlight that our current reliance on fossil fuels is driving up CO2 and methane emissions, which of course directly worsens global warming. On top of that, you've got economic instability and high inflation making power ridiculously expensive. And then, think about regions with really complex geographies. Take the Philippines, for example, with its thousands of remote islands. Transmitting and distributing power across all that water is incredibly difficult. All of these constraints drive a super urgent need for new, localized, and sustainable power generation methods that don't rely on constant, endless fuel deliveries. Section 2, Torque, Power, and RPM. Now, before we look at the complex systems designed to actually solve these energy issues, we need to quickly equip ourselves with some foundational physics. First up, torque. Think of it simply as a motor's ability to generate rotational force. It's usually measured in Newton meters or pound-feet. A really great everyday analogy is riding a bicycle. Imagine you're pushing down incredibly hard on the pedals, you're in a super heavy gear, and you're trying to muscle your way up a steep hill. That heavy, pushing, rotational force you're applying, that is torque. It's basically the brute force of the rotational world. Next up is power. Power is the measure of a motor's ability to actually do work over a period of time. Mathematically speaking, power is calculated as the product of torque and angular velocity, which we all commonly know as RPM, or revolutions per minute. So if torque is that brute pushing force we just talked about, power is how quickly and consistently that force actually gets the work done. And here's the kicker. You need both of them to generate electricity efficiently. Section 3, Fuelless Generator System Design. Let's take those foundational definitions and actually apply them to a customized mechanical gearbox system detailed in our source research. This setup brilliantly illustrates the theoretical design of a fuelless generator. Just follow the flow here. It starts with a rechargeable 48-volt external battery. That battery powers a much smaller 600-watt gear motor. Then, that motor drives a gearbox, which mechanically steps up the rotational dynamics to drive a way larger 5,000-watt AC generator. Finally, a portion of the electricity generated goes right to a rectifier. That converts the AC power back to DC to recharge the battery, creating this really clever recycling power loop, while the rest of the juice goes to the actual load. Now, to make a little 600-watt motor successfully turn a giant 5,000-watt generator, we have to look closely at the gears themselves. As our sources point out, Newton's third law of motion dictates that if a driving gear exerts force on a driven gear, that driven gear exerts an equal and opposite force right back. The law of gearing basically says that by manipulating the size of the gears and the number of stages in the mesh, you can physically trade speed for torque, or vice versa. It's all about passing it through a fixed pitch point. So the absolute crucial point is the math behind this. Look at the input motor. It operates at a very, very slow 50 RPM, but it produces a massive 120 Newton meters of torque. The catch? The generator needs to spin at a rapid 1800 RPM to actually produce power. That's where the customized gearbox sits in the middle. It takes that massive input torque and trades it away, reducing it down to 26.5 Newton meters, but, and this is the genius part, it successfully steps the speed all the way up to the required 1800 RPM. It is a perfect mechanical trade-off to meet the generator's exact needs. Of course, anytime you're evaluating an energy conversion device, you absolutely must look at its efficiency. The fundamental formula engineers use calculates efficiency by taking the total output of the system, dividing it by the input, and then multiplying by 100 to get a percentage.
Simply put, this tells us exactly how much usable energy a system yields compared to what it consumes.
Applying that standard formula to the specific theoretical parameters of this fuelless generating system, the researchers report a really fascinating figure. By taking the 5,000-watt output of the generator and dividing it by the 600-watt input of the initial gear motor, the researchers calculate an incredible 833% theoretical efficiency. Yes, you heard that right, 833%. Now, it's a very striking theoretical calculation, but it really highlights the highly ambitious design parameters of utilizing mechanical advantage in this specific layout. Section 4. EV motors and power curves. We've just seen how physical gearboxes manipulate torque and speed. Let's move on and see how this builds our understanding of electric vehicles, which achieve similar manipulations but use advanced electrical software instead. When you press the pedal in an electric car, the motor actually operates in distinct phases. First, right from a standstill, it's in what's called the constant torque region, delivering maximum rotational force for that instant, quick acceleration we all know EVs for. But as the car speeds up, it hits its base speed. Beyond this point, the motor transitions into the field weakening and constant power region. Here, the brute force drops off, but the motor maintains maximum power to keep pushing the car faster and faster. Now, we have to distinguish between the types of force an EV can actually handle, because there is a huge difference between peak torque and continuous torque. Peak torque is the absolute maximum power the motor can produce, but it can only do so for really short bursts, maybe 30 seconds. If it sustains that peak for too long, the high stator currents will actually cause thermal damage, like it'll literally melt the wires, and absolutely nobody wants a melted motor. Continuous torque, on the other hand, is a lower threshold of force that the motor can safely sustain indefinitely without any risk of overheating. Now, what's really interesting about this is how EVs handle those high speeds. Instead of using a physical multi-speed transmission like a traditional gas car, EVs use a technique called field weakening. The system purposefully adjusts the currents in the stator to create a magnetic field that actively opposes the permanent magnets in the rotor. This super clever electrical manipulation actually reduces the net magnetic field. The result? It allows the motor to spin much, much faster. This extends its speed range for highway driving, even though the total torque capability is decreasing at the same time. Section 5. Redefining sustainable energy. Let's take a step back and look at the broader, real-world impact of everything we've just learned about managing power and motion. What you should really take away from all this is that whether it's through the heavy, physical gears of a localized fuelless generator or the advanced software managing stator currents in a modern EV, optimizing energy conversion is absolutely the key to our future. Mastering torque and power physics allows engineers to design systems that operate with zero greenhouse gas emissions. That paves way for 100% decarbonization. It reduces costs, it completely eliminates the need for fossil fuels, and ultimately it creates sustainable systems that don't just depend on whether the sun is shining or the wind is blowing. And so I'll leave you with this final thought. As technology rapidly advances, how will our continued mastery of this delicate balance between torque and power ultimately drive the 100% decarbonized energy grids of tomorrow? The fundamental physics, well, they stay exactly the same, but the engineering possibilities, they're completely boundless. Keep learning, keep questioning, and I really hope this explainer gave you a clear window into the fascinating mechanics powering our sustainable future.